let's do this problem. We will do it both ways, Newtonian mechanics and Lagrange.
Using the A Newtonian and B Lagrangian.
Okay, let's do the Newtonian one real quick. There's two masses. How many equations should we get? Done. Let's do this real quick. Mass 1 should have sigma fx and sigma fy. Mass 2 should have sigma fx, sigma fy. Fy goes away. I'm left with T. Oh, it's frictionless, right? Oh, so we're not even worrying about friction. So that's T goes this way. T2 goes that way. So this will be plus. We all know T1 equals T2, right? So I'm just going to replace it with just T. For sigma Fy, we'll just have N minus M1G. And they say masses are equal, so I'm just going to ignore. And then this one will be minus T plus mg. And this system is being accelerated. So that means sigma fx is going to be ma, and this is also going to be ma, right? They're both positive. ma equals T, ma equals minus T plus mg. I'm looking for acceleration, right? So I can add these two equations. So I want to get rid of the T. mg. M's get canceled, and I get A equals G over 2. Now let's do the Lagrange formalism. That's going to be new. So step 1. What was step 1? Choose your coordinate system. Actually, no, choose your generalized coordinates, which means you don't have to choose X, Y. What that means is you have to choose your Q's and Q dots. Okay, so in this case, what do Q's and Q dots mean? So our generalized coordinates is there anything in the Y that I necessarily need? No, I only need X's and X dots. Then my next thing was I have to write my T. T I know is 1/2 mx dot squared, correct? But how many m's do I have now? So I have to do it twice. Okay, now comes number 3. We have to figure out what potential we are using. Are we using a conservative system?
Yeah.
Is there friction there? So it is a conservative. So I don't have to worry about anything except your potential energy will be only a function of mgh. Now, but however, be very careful. We are talking in general when we talk about h's, we are always referring to h with respect to the ground. In this case, your x, as your x increases, your potential goes down. Why? Because your x is this x. So as your x will go, in general, when we do these problems, what do we have? We have a ball falling, and we consider the height with respect to this 0, and this is the height. As height goes up, potential goes up. As height goes down, potential goes down, right? That's our normal way because we choose our origin to be on the ground. In this case, where are we choosing the origin matters. Because what we're saying is as delta x goes up, potential energy goes down. Do you see it? Because it is now a connected system. You can't just ignore it. Does that make sense? So in this case, what will be my potential? Opposite to x. As x goes up, your potential goes down. Okay, so now the next fourth step is to write your Lagrangian. What will your Lagrangian look like? Well, in our case, my p's and my both m's are the same. Can I combine them to write this? So then my Lagrangian will become t minus v, or mx dot squared plus mgx. Okay, so now that we have our Lagrangian written out, which one of these two equations should we use? The 1 or 2? 1. Good. So we are going to use equation 1. However, that was an equation that was written for generalized coordinates. What would that equation look like for this scenario? Number 5. So we chose equation 1. What will that look like? D over dt, partial L over partial x dot, very good, minus partial L over partial x equals 0. For a second.
That is a 2 there.
So just watch. Since m cannot be 0, the rest of the equation must be. What is x double dot a? Compare them to give us the same answer. As it should be. The hardest part in doing these kinds of problems is to figuring out what t and v are in the different scenarios. Once you have that figured out, it's just a matter of differentiating it. That's it.